It's time to export the knowledge. Today's video we're going to be looking at the hyperbolic locus. So hyperbole or a hyperbola, not hyperbola or hyperbole or whatever you want to pronounce it as. It's hyperbola. Now, what is a hyperbola? A hyperbola is something like this, and we'll express the general form in just a second, but this is just to make sure that you understand what a hyperbola is and what it looks like. So y is equal to 1 over x. So let's start with a table of values, and we'll just plot it onto this graph here. So let's start with x is equal to 1. So we can sub it in, and we'll get 1 over 1, so y is also 1. Okay, easy enough. Alright, x equals 2. So 1 over 2, that's a half, so y is a half. There's going to be a pattern occurring here. So x equals 3, it's going to be equal 1/3. What is the relationship between these two? They're the inverse of each other. So what do you think is going to happen to the 1/2? It's going to be the inverse. If we have 1 and we divide it by a half, we can times by 2 over 2, and we'll get 2 over 1, which equals y, 2. And we can try this with negative values, and you can see that it'll also stand true. If x is -1, then y is -1. If x is a -1/2, y is a -2. So let's grab these values and let's plot them. So let's say here is 1, 1, and let's put x equals 2 like here, and then x equals 3 here. And let's go up to a half, and you can see it's doing this curving type of thing. So let's do negatives now. So x is equal to -1, -1/2. We'll do -2, -3, and you can see it's sort of getting closer and closer to the axes, but they never actually reach. What is it going to end up happening? I'm going to do something like that. And it's going to try and get closer and closer to the axes, but it's not going to happen. This is known as the rectangular hyperbola. The reason being is that the asymptotes, what this line is ever approaching to, makes a right angle in between them. So the asymptotes for this particular hyperbola is going to be x equals 0 and y equals 0. And you can just see that that's just the axes. So with that in mind, let's start doing stuff with locus. So the way you do it in locus is that you're going to have a focus, and it's going to be a times e comma 0, similar to the ellipse, but e is going to be greater than 1 this time. And the directrix is going to be a over e, again, just like the ellipse. And our condition, of course, is going to be from P to F is going to equal the eccentricity times P to M. So just remembering what that looks like, here's our directrix here. There's our M point. Let's say this is P, and there's our focus. You can see how the eccentricity has changed the length. Let's set up our locus conditions. So here's our locus conditions. Let's put the distance formula. So the square root of x minus a times e squared plus y minus 0 squared is going to equal the eccentricity times the square root of x minus a over e squared plus y minus y squared, remembering that the directrix point M shares the same y value as point P. So on this side we can simplify it down. This becomes 0, and then the square root and the square cancel each other out, and we're left with e times x minus a over e. Could expand inwards, but it's better to just leave it for now and square both sides first. Do x minus a times e squared plus y squared is going to equal e squared lots of x minus a over e squared. Now we're going to expand both sides. We're not going to expand the e squared into it yet. So we're going to have x squared minus 2aex plus a squared e squared plus y squared is going to equal e squared lots of x squared minus 2ax over e plus a squared over e squared. I'm now going to expand the e squared inwards, so we'll get e squared x squared minus 2aex plus a squared. There's some cancelling here and here. I'm now going to move everything with an a in it over to this side, and everything with an x or y in it over to this side. So what we'll get is a squared e squared minus a squared is going to equal e squared x squared minus x squared minus y squared. I'm now going to factor a squared out on this side and x squared out on this side, so we'll get a squared lots of e squared minus 1 equals x squared lots of e squared minus 1 is y squared. And then I'll divide both sides by a squared lots of e squared minus 1, and we will get the form that we're looking for. Get 1 equals x squared over a squared minus y squared over b squared, where b squared is equal to a squared lots of e squared minus 1. There's our form here, our general form for the hyperbola. So now that we have this general form, we need to find the asymptotes. So remembering the asymptotes is what this line will approach to. What I'm going to do now is I'm going to take our general formula here, and I'm going to make y the subject. So the first thing that I want to do is I'm going to move this x squared over a squared onto the other side here, so we'll get minus y squared over b squared is equal to 1 minus x squared over a squared. I'm now going to take out the minus on this side. Get y squared over b squared is going to equal, and I'm going to swap these two around, so the positive terms at the front, x squared over a squared minus 1. And now I'm going to times by b squared, so I'm left with y squared is equal to b squared over a squared x squared minus b squared. Now I'm going to square root it, so y is equal to the square root of b squared over a squared x squared minus b squared. So wouldn't it be great if this b squared here just disappears? And that way we'll have a lot of cancelling, and we'll be left with y is equal to b over a x. Wouldn't it just be nice if that was true? We assume that x is heading towards infinity plus minus infinity. What's going to happen? This term here is going to be really, really big, and then this is going to be something proportionately small. So because b squared is just a constant, and x is going to be something absolutely massive, we can drop the minus b squared, because it will make no difference when we square root it. So then we're left with this. And of course plus minus because it's a square root. And what this is our asymptotes. Here's our hyperbola, for example. There's our asymptotes. And that'll be b over a x, and this will be negative b over a x. So there's one last thing that I want to do before we go, and let's do an example question. So let's do x squared over 9 minus y squared over 16. I'm not going to work with the eccentricity or any of that business. I'm just going to sketch it. So now that I have my xy plane, I'm now going to sketch this as best as I can. So the first thing that I need to do is I need to work out what my a and b is. So a is going to equal 3 and b is going to equal 4. Now, in order to sketch this, what you can do is that you can draw this dotted box. So all you have to do is start from the origin, go up b values, so to where the 4 is, and go across to wherever the a value is, so 3, and then you can go back down, and you can go down the b value, and you can just continue this dotted box. So there's minus 3, and you'll create this box here. Now obviously on a grid this will be a lot more symmetrical, but let's pretend that this is perfectly accurate for the sake of explanation. So now there's a couple of key points. You can say that here is the two vertexes of my hyperbola, and you can grab your ruler and you can join the two corners of this box together with a straight line. And if this was accurate, it would go through the origin, but no matter. So there's our asymptotes. And now, all I have to do is I need to sketch this in such a way that my line gets closer and closer to the asymptotes, but never actually touches. So it'll look something like that. So you can see that it has the general kind of form, but now the angle has changed and the asymptotes has also been rotated. So now you need to make sure that you label everything. So this hyperbola is x squared over 9 minus y squared over 16 equals 1. And then you need to label your asymptotes, which is going to equal y equals 4 over 3x, and y is equal to negative 4 over 3x. And there's your asymptotes. So now that we've actually sketched it, might as well get our directrices. So you know, 16 is going to equal 9 lots of our eccentricity minus 1. And we just have to solve for e squared, so we'll divide by 9 and we'll plus 1, and that'll equal e squared. So 9 plus 16, that's 25 over 9 equals e squared. So e is equal to 5 over 3. So our directrices is a over e. Our a value is 3. and then we're going to times the reciprocal, which is 3/5 of our eccentricity, and then we'll get 9/5. So we can put wherever 9/5 is, so that's really close to 2 but not quite. So it'll be around about here and here, let's just say. And you would label your directrices as well with 9/5 and -9/5. Our focus is going to be our eccentricity times the A value, so it's actually going to be at 5. So assuming that that's 5, that's also our focus. And there's -5, so there's our other focus. So just like all the other Locus videos, you can get a link in the description to the Hyperbola Locus in Desmos, and you can actually play around with it. In the next video, we'll show how to change the position of the locus. Of course, you can take a look at everything that I've done in this little folder here, and you can also turn off the square for sketching if you just want to look at the graph there. You can also view the eccentricity as capital E here. So that's it for this video. If you have any questions, feel free to contact me on social media or leave a comment down below, and I will see you in the next video.